We've been learning so far that all numbers which can be expressed as the ratio of two integers are called rational numbers. So we can say that all numbers which can be expressed as p by q, where of course the denominator q is non-zero, they are all called rational numbers. So we can consider that 2 by 3 is a rational number. It's a ratio of two integers. The whole number 5 is also a rational number because it can be expressed as 5 by 1, or 7 by 10 is a rational number. So all integers, whole numbers, decimals, whichever numbers which can be expressed in this form are called rational numbers. So let me assume that I have a container full of all those rational numbers. This is a container which consists of only rational numbers, all those numbers which can be expressed as p by q. So all these numbers are all contained in that container. Alright, and whatever rational number you could think of is contained in this container. So now we are just going to try performing the operations of addition, subtraction, multiplication, and division on these rational numbers, and we're just going to explore what happens to these numbers. So just take, for example, take the same 2 by 3. Take 2 by 3, and if you're going to add it to some rational number, say 1. Right, what is the result going to be? Now let's just perform this, being very simple. Now 1 can also be expressed as 3 by 3, isn't it? Or you find the LCM, whatever it is. So this is the addition of 2 by 3 plus 3 by 3 is going to be equal to 5 by 3, which in turn is also in this container. 5 by 3 is definitely in the container of rational numbers. Now just try subtracting, or 2 by 3 plus it's either subtraction or addition of minus 1 to 2 by 3. This is 2 by 3. 2 by 3. So the addition, subtraction can also be looked at as addition, isn't it? So it's the same. If you prove for addition, if you prove some facts for addition, it holds good for subtraction also. Suppose I want to subtract 2 minus 5, I can also express it as 2 being added to minus 5. So addition and subtraction are one and the same. So you prove something for addition, it is proved for subtraction. So having done the groundwork, let us now explore what happens if you add a by b, any rational number, to any other rational number a1 by b1. So we're just expressing it in the general form, and we are going to find out what happens to this when you add or subtract. So just imagine, if you're going to do minus, it's going to be subtraction, isn't it? So we're just going to now add and see what is the result of this. So a by b plus a1 by b1. You normally, what we do, we take LCM b1, and the numerator is multiplied by ab1 plus a1b. Now each of this a, b, a1, b1 all are integers. So what is a, b1 going to give me? This is also going to be an integer, and a1b is also an integer, and b1 is also an integer. So the sum of two integers makes your numerator, which is an integer again, and the denominator is also an integer. So this can be said to be in the p by q form, isn't it? This is in the p by q form. So what we conclude is that addition of any two rational numbers, or subtraction for that matter, like we mentioned here, subtraction of any two rational numbers also gives us a rational number, which is, it would be contained in the same container from where we picked up these rational numbers. Now the point to be observed here is, since this is a rational number, b is not equal to 0 and b1 is also not equal to 0. So the product of b1, two non-zero numbers, will also not be equal to 0. So q is not equal to 0. This fact is also ascertained here. Now let's go to multiplication. Since we have done addition, let's think of multiplication. Consider any two numbers. Suppose I take just integers. 3 multiplied by 5 is also 15. Right? It is a rational number. What if you multiply 3 and 1 by 5? This is multiplication of 3 and 1 by 5 gives you 3 by 5, which can otherwise be called as 3 divided by 5. So I'm going to say the same rule here. If you, just like we mentioned here, if you prove something for addition, it is proved for subtraction also. The same rule applies here. If you prove some facts for multiplication, it can also be considered the same for division. So having this in mind, let us now generalize this process of multiplication and division. Consider any two rational numbers once again. Let it be a by b. Sorry, let it be a by b and something else, maybe this time a2 by b2. So how do you go about multiplying? You just get a2 by b2. So once again, this a and a2 being integers, your numerator is definitely going to be an integer, and b and b2 being integers. Remember, we have taken rational numbers, right? Rational numbers are the ratio of two integers. So b and b2 being integers, your b2, the denominator of the new number which we have created by multiplying these two rational numbers, is also a rational number which can be expressed as p by q, the ratio of two integers. And once again, I point out this fact that since it's a rational number, here b is non-zero, b2 is non-zero, so b2 is also non-zero, which says that q is not equal to 0. So we have ascertained the same fact for multiplication and division, that if a container consisting of rational numbers is being picked up one by one and the operations of addition, subtraction, multiplication and division are performed, the result so obtained will also be a rational number. So if I call this a set of rational numbers, if I call this container a set of rational numbers, then I can say that this set is closed. It is closed under all these operations of multiplication, subtraction, division and addition, right? So this set of rational numbers is closed under these operations, and this is what I wanted to specify or point out in this video. I hope you followed. Thank you.